So at this point, we are going to start studying the discrete random variables. And how do we model a discrete random variable if we were defining a probability mass function for it? And that probability mass function was denoted by lowercase p of x, which represents the probability of the corresponding random variable to be equal to that arbitrary value of lowercase x. So please take note that the probability mass function is not a function of the random variable. It is a function of real values, x, but that function represents the random variable x. So we are using that probability mass function to define the random variable. It is not a function of that random variable. It belongs to that random variable. Another function to represent the probability information on the random variable is the cumulative distribution function, and that is denoted by capital F of x, and capital F of x is the probability of the random variable to be less than or equal to x. So what is the probability of that random variable to take any value less than or equal to x? So again, we are talking about an arbitrary real value here. That is going to be the capital F of x, which is the cumulative distribution function. Actually, according to the axioms of probability, the cumulative distribution function should be a non-decreasing function of x. I am not saying it is increasing. The rule is it should be non-decreasing. It never decreases, but that does not mean that it is going to increase always. So let's solve an example for a discrete random variable. Again, based on the previous example, we are going to toss two fair coins, and we are defining the random variable x as the number of heads appearing. We are going to write the probability mass function and the cumulative distribution function for that random variable, and we are also going to draw these functions. So why we are doing that? We would like to understand the probability information on random variable x. And the cumulative distribution function here gives us the whole probability information on any random variable. Here, for this example, the probability mass function also provides the whole probability information, and they are one-to-one convertible. So if you know the probability mass function, you can also determine the cumulative distribution function, or you can go back from cumulative distribution function to probability mass function. But for this example, and for many examples that you learn in the undergraduate courses, it is still the same. However, there are some advanced examples where the probability mass functions or the probability density functions for continuous random variables cannot fully represent the whole probability information on a random variable, but the cumulative distribution functions, they store all information on probabilities on that random variable. Okay, so we have already determined the possible values that the random variable can take on 0, 1, and 2. And the probability mass function of random variable x, which is p of lowercase x, gives us the probability of our random variable to be equal to any x values. And as we have said that this x value, lowercase x value, can take on 0, 1, or 2 value. And in that case, the respective probabilities on random variable is going to be 0.25, 0.5, and 0.25. And elsewhere, we need to indicate that elsewhere the probabilities are 0. So our random variable cannot take any other value than these possible 3 values. And the drawing of this probability mass function is what? So at 0, 1, and 2, we have probability masses as described in the probability mass function here. So p of x are going to be 0.25, 0.5, and 0.25 here. And anywhere else, the probability masses would be 0. Now, check the cumulative distribution function, which gives us the probability of our random variable to be less than or equal to x. And that is basically a cumulative version of the probability mass function. So for any x value that is less than 0, what is the probability of our random variable to take on a value that is less than or equal to that value? Okay, as long as that x value is less than 0, there is not any probability mass value on the left-hand side, right? Therefore, we should say that that cumulative probability is 0. Now, as you move forward, if you come to the point of 0, the cumulative probabilities will increase to 0.25. And between 0 and 1 values, where 0 is inclusive but 1 is not included, the cumulative probability will become 0.25. So for any value within this interval here, the total probability mass on the left-hand side will always be 0.25. And when you include 1 to that, the cumulative probability will become 0.75. And within the interval of 1 and 2, where 1 is included and 2 is not, the total probability on the left-hand side will be 0.75, which is the sum of these two probability masses. Finally, when you reach to 2 from that point until infinity, the total probability on the left-hand side will always be 1. Therefore, the cumulative version of the probability mass function would be in the form of a stair-shaped function, starting from 0 and reaching to 1 in a non-decreasing fashion. But the shape of the function would be like a staircase. Now, we can also define the expected value for discrete random variables. The expected value of a discrete random variable x is equal to the potential or the possible values that the random variable can take multiplied with the probability mass values on that value, and we are summing these values up. So basically, we know that the probability masses, they need to sum up to 1. They can be assumed as weights for the possible values, right? So we are multiplying the possible values that the random variable can take with the respective probability mass value as weights. So this is basically somehow a weighted average of the potential values that the random variable can take. And each value is basically weighted by the respective probability on that random value. For the previous example, I can calculate the expected value as multiplying 0 with the probability mass value of 0 plus 1 with the probability mass value of 1 plus 2 with the probability mass value of 2. And in that case, I can define the expected value as 1. Now, another measure of interest about a random variable is called the variance. And the variance is a measure of spread. So it is a measure indicating how the potential values that the random variable can take are distributed or spreaded over the real numbers line. So we are basically measuring dispersion here. So the classical formula for the variance is what? It is basically the expected value of the squared deviations of the potential values that the random variable can take from the expected value. So expected value is also called the average value of that random variable. So we are interested in the difference between the potential values and the average value. And the square of this is called the squared deviation. And variance is basically the expected squared deviation. How can we calculate that? First, we need to calculate the expected value. So variance calculation requires calculation of expected value. Then we calculate the squared deviations from the expected value for each possible value that the random variable can take. Now, this time we are taking the weighted average of the squared deviations with respect to the assumed probabilities on these values. Another formula for the variance is a more convenient formula, is equal to the expected value of x squared minus the square of the expectation. And how can we find the expected value of x squared? This time we are calculating the square of the possible values that the random variable can take on and take a weighted average of them with the probabilities assumed on these values. And the square of the expectation is calculated here. Again, you require the calculation of the expected value for the second part of this formulation. Now again, for the same question that we have solved earlier, we are going to calculate the variance of x. And that is going to be, according to the convenient formula, expected value of x squared minus square of the expectation. The expected value was already calculated as 1 in the previous question, so all we need to do is to calculate the expected value of x squared. And for each possible value that the random variable can take on, we calculate the squared values 0, 1, and 4. we take the weighted average of them with the respective probabilities that are being assumed, and that makes a 1.5. 1.5 minus the square of the expectation gives you a 0.5, and that is the variance for this random variable. Okay, now on expectation and variance, we have some important identities which can easily be proven for discrete random variables, and the same proof can also apply for continuous random variables as well. Now, here we have a and b as real numbers, and ax plus b is basically a linear function of random variable x. So we are multiplying the random variable x with a multiplier here, which is called the slope of this linear function, and b is called the intercept of this linear function. So the question here is this: what is the expected value of a linear function of a random variable? It is always equal to the linear function of the expectation. So here, in this linear function, both the multiplier and the increment, or the slope and the intercept, they can get out of the expectation, and the expected value of a linear function of a random variable becomes the linear function of the expectation. Actually, I am not going to explain the details of the proof here. The proof is just given for the sake of completeness. This is just a repetition which we are going to utilize in the future weeks, and this is just for remembering this identity. And another identity is what? It is the variance of ax plus b. Again, we are interested in the variance of the linear function, but unlikely to expectation, the variance of the linear function of a random variable is not equal to the linear function of the variance. In this variance formulation, the intercept term is not important at all. Okay, so when you add a value to the possible values of that random variable, to all of them, if you add the same value b, then the dispersion or the spread of the potential values over the real line does not change. So they are still taking this time different values which are shifted by b, but at the same dispersion. Okay, the spread of the potential values are going to be the same. Now imagine this: you have a die. On the face of the die, you have integers from 1 to 6. Now, what I am asking you to do is, instead of writing integers from 1 to 6, please add 1 million to each face. Okay, so you are going to develop a new die on the faces of which you will get integers from 1,000,001 to 1,000,006. Now, of course, the average value you get when you toss that die is going to change. However, the variance is going to still be the same, because the spread of the values are still 6 consecutive integers. Okay, so the variance is not affected by this shift term, by this intercept. However, the slope affects. If you multiply the values on the face of a die, for example, with 5, then the values are going to be spreaded over a larger part of the real line, right? So in that case, we should say that the variance of ax plus b is just going to be equal to a square of variance x, which means the multiplier term gets out of the variance as squared, but the additive term, the increment, is not affecting the variance formulation.